All right, our next part of logistic regression is to conduct some formal inference and see what's necessary to make that valid. So conducting hypothesis tests and creating confidence intervals. So hopefully you've already read through this document and put all the R code in and tried it out. I'm just going to touch on some highlights here. So we go back once again to the medical school acceptance example, and we create this variable GPA 10, so we multiply all the GPAs times 10. And the reason for that is that basically when the input then increases by 1, we're talking about a 1/10 of a point increase in GPA, which just makes more sense prediction-wise. So for example, if GPA 10 goes from 35 to 36, that realistically is increasing GPA from 3.5 to 3.6. Okay, so we fit the model, and just by way of reminder, based on this summary output, we're saying that the log of predicted odds of success of being accepted is now a linear function of GPA. So based on the model output, we could write the model that way. We could also put it in probability form if we wanted to. So basically, we have the same kinds of interpretations we've done before. We have this p-value that's got the 3 stars. It's less than 0.001. It's very small. So we have strong evidence of a log linear relationship between being accepted and GPA 10. We can also create a 95% confidence interval, so we have our beta 1 hat here, and we have standard error here for that beta 1 hat, and then the multiplier 1.96 goes with the fact that we have a confidence level of 95%, and we can create the confidence interval in the usual way. Now, interpretation-wise, remember we have to do exponentiating, and we're talking about odds ratios when we do that. So the same way that we could exponentiate the slope that we learned about earlier to get an odds ratio, we can just exponentiate the endpoints of the confidence interval, right? So basically this is giving us an interval of what the odds ratio might be. And the way we interpret it in this case, the odds of being accepted to medical school are between 1.3 and 2.4 times higher for each 1/10 point increase in GPA. And then you have the code there to come up with the confidence intervals. So our hypothesis test that we're conducting, we have a single predictor here, GPA, and we're basically determining whether the slope or the coefficient on that predictor is 0 or not. So our test statistic is a z-score here, where we take the estimated beta 1 coefficient over the standard error, and it talks about a reasonably large sample size. Talk to 5 statisticians, you might get 5 different answers on what that is. There are some guidelines out there about it. Don't want us to get caught up in that. The independent random outcomes, as you've probably seen, we bring up later in this document. But we have this z-score called a Wald statistic, and then again we just went over how to compute the confidence interval. Realistically, we don't really need to know the multipliers for z-star based on the confidence level. We just let the computer do it. Okay, this next section is basically talking about how the parameters or the estimated coefficients are arrived at. We're not doing least squares regression, so we're not minimizing the sum of squared residuals in this case. We're actually minimizing this thing called deviance. So L is a quantity called the likelihood, and basically the idea is that the computer is sort of saying, okay, what if my parameters were this beta naught and this beta 1? What is the likelihood of having this set of observed data? and then it moves to a different combination of beta 0 and beta 1 and says, okay, with these beta 0 and beta 1 values, what's the likelihood of the data that we have? And it just, as computers do, goes through a bazillion possibilities in no time flat, and it figures out the parameters that result in the maximum highest likelihood for the given data. Now the thing is that what we really consider instead of maximizing the likelihood is minimizing this thing called deviance. Again, they're equivalent to each other. If you maximize L, that's equivalent to minimizing negative 2 log L, which is the deviance. And so we have a null model that basically has the same probability of success for every value of the predictor. And that probability of success is the overall probability of success in the sample. And then we compare deviance values and look at a chi-squared distribution to come up with our p-value. So again, we're not using a normal distribution, we're not minimizing the sum of squared residuals, but we have kind of something that's analogous to that nested f-test. So here for our model output, and you might have noticed these in your model output and I haven't mentioned them up till now, we have the null deviance based on the null model and the residual deviance based on the model with GPA in it. And our test statistic is actually the difference between those two, and then we have 1 degree of freedom in this case because we're looking at a difference of 1 predictor from the null model to the what we could call and will call soon the full model. And R can calculate the p-value based on a chi-square distribution, and the p-value in this case is very, very small, so we have, again, very strong evidence of a relationship between the GPA and the medical school acceptance. So we can use this other test on the same pair of hypotheses. So we have the Wald statistic and that test, and now we have this likelihood test. And basically they're equivalent. This test is called the likelihood ratio test. You might also see it, I've not seen it, but you might see it called the G-test, and then often it's called the drop-in deviance test, which makes sense if we're calculating the drop or the how much the deviance decreases by from the null model to the GPA model or the 1 predictor model. And so it mentions here that we don't always get the same p-value from those 2 tests, even though they're basically testing the same thing. But if you get any, or especially a big discrepancy between the two, then the p-value from the likelihood ratio test is the one that you want to go with. All right, I don't think there's anything in this example that I wanted to mention. It's, I hope, pretty straightforward, but anything you have questions about, just send me an email and let me know. Now, one thing here with the migraine headache example, remember our data was basically in a 2x2 table, which not only meant we had to change the syntax on the GLM command, but it also means that basically this null deviance is our G statistic. So just FYI, when you have that situation where your data is in summary in a 2x2 table already in your data set. Now here it mentions the p-value for the slope coefficient being about 0.1. FYI, if you did the chi-square on this 6.8854 null deviance, you would get also 0.01, it's 0.008-ish. So they pretty much agree in this case. And again, if you run the code on these confidence intervals, you should get the 1.22 and the 4.22 in this interpretation sentence I have here. And just a reminder here that in addition to odds ratio, we can think about probabilities as well. And the computer can find those, but I just wanted to remind you what the calculations are. So remember that to get from odds to probability, we take odds over 1 plus odds, and that gives us probability. All right, now let's talk about assumptions. So in order to do this kind of inference where we run these hypothesis tests or we create confidence intervals, we should have met the assumptions. And what are the assumptions in this case? So they are not the same as they have been with linear regression. We're not talking about having constant variance or errors that follow a normal distribution. What we actually have is this idea of a spinner being a reasonable model for what's happening. So in this graph on the left, we did ordinary least squares regression of MCAT versus GPA. And our assumption when we create that model is that, for example, these outcomes for GPA of 3.6 are roughly normally distributed. Whereas in the logistic model, we're talking about this spinner idea. So we're saying, do the outcomes behave as if they were generated by a spinner with a constant probability of success, and that value of the probability of success might be different at each different GPA, but that's the way the outputs should behave. So for example, if we had 10 outcomes, maybe 7 out of the 10 in our sample resulted in being accepted, and maybe 3 out of the 10 resulted in not being accepted. And the model itself is predicting a 0.6 probability of being accepted for a GPA of 3.6. So basically, what we need are for our outcomes to be random and independent in order to be able to conduct inference, and that pretty much means that a spinner model has to be reasonable. And so unlike before where we could look at a quantile plot or a residual versus fit plot, there is no plot we can look at to determine whether randomness and independence are met. We just really have to think about how the data were produced. And again, you can kind of go down a rabbit hole with this, but if you have random assignment or random sampling, or gosh, imagine if you could have both, then you're pretty much set and your conditions are met. Otherwise, you have to just think about it. And I'll give you at least one or two to practice with so you can kind of try it out for yourself. FYI, I won't be including this randomness and independence or whether assumptions are met on the quiz. Then the other thing, in order for your model to be sort of a good one, is, of course, it should be logit linear. In other words, the log odds of success should be a linear function of your predictor. So depending on what you have in your data set, you have different ways that you can sort of check this, and you can check it with a plot. And so I gave the example here of the Putz data set, which was a nice one because at each different distance there were lots of different values of made or not made, and so we could come up with the empirical logit values. And so if we just plot those values, they definitely appear to be linear. So that's a way we can check if we have a lot of response values for each value of x and our predictor is quantitative. Now, as it mentions up above, if the predictor is binary, then linearity is pretty much automatic because we only have the 2 points, and we did an example like that. Now, this third situation is a little bit more complicated, that if we have a quantitative predictor and we don't have a lot of responses for each value of the predictor, what we can do is kind of group things together and take average values of the predictor and get logits, empirical logits that way for each group. And just note to self, we are going to be using this adjustment. We can add a half to the numerator and 1 to the denominator when we're coming up with those observed proportions if our group sizes are kind of on the small side. And then we can plot the group p-hat values, the logits of those, against the mean values of the predictor, and see if that appears to be linear.